Hello and welcome back to the class once again. Now we will move after activated carbon. In this class we will just consider about the different materials, so which are inorganic materials and which are hard in nature. So metallic hard materials, how we find and what are those metallic hard materials, how we define these as a different types of materials. So inorganic chemistry can contribute through the development of these materials is some aspect of the material science where we can use the metals and its corresponding oxides or nitrides or any other thing as typically very hard materials. So these hard materials are nothing but simply the carbides first, starting from your calcium carbide or any other, then borides and silicides. So these three together we will now just consider for this discussion in this particular class, where we will consider that their corresponding carbides, borides and silicides, the anionic part is now we fixing of the elements in subgroup of 14, 15 and 16 of the periodic table. Along with that, we can also consider other two based on the metal ion thorium as well as uranium, because the thorium carbide and uranium carbide are also very high metallic hard materials, metallic hard materials of these, because this hardness is a scale where that particular hardness can be judged for these metallic hard materials is almost without exception between two quantities of thing of hardness. One is the corundum, another is the diamond. So between corundum and diamond you will be able to get the corresponding hardness. We can fix the hardness on Mohs scale. We also measure the hardness for these metallic hard materials, and this basically between corundum and diamond. So in the range of 9 to 10, you see that we have a scale of 0 to 10 basically, and silicon carbide we know that it has also the corresponding very high hardness. So on the Mohs scale, at the upper side only, at the range of 9 to 10 only, we will be able to consider these materials, the inorganic, metallic, carbides, borides and silicides can be considered as the typical metallic hard materials of use, and they basically use also comparable electrical and thermal conductivities, which are also very important characteristics of these hard materials, because these are not metals. And also basically when you consider that is a carbide compound or a boride compound or silicide compound of the metal ion, what do you think that these are basically inorganic compounds where the anionic part or the corresponding part of carbide, boride and silicide is there, but still we have the corresponding hardness in the range of the metal, as well as the thermal as well as the electrical conductivity is in the range of the corresponding metals. So they have also very high melting points, that is as a result, because some of them are very high melting and high chemical resistance. So these fundamental properties of metallic hard materials give us some idea that how quickly we can use them for some different useful purposes. So these metallic hard materials therefore are very useful for industrial preparation, their property improvement and applications. So first we will see how we get the metal ion based carbides. So how we bring that corresponding carbon for making those carbides. So basically if we have seen that how we make the activated carbon from the different carbon sources or the source of coal, source of pitch and all these things. So if we have this superior quality of carbon black or some inferior quality of carbon like lamp black, that can be typically used for the manufacturing of these metal carbides, because metals or the metal oxides, because directly we can use those metal oxides from the natural sources, that means the ores basically. We know as iron, the iron is the corresponding ore is available as the corresponding oxide ore. So if that oxide ore directly with some preliminary purification or preliminary screening only can directly be used for reaction with the carbon, we get it at high temperature, that means 1200 to 2300 degrees centigrade, we get the corresponding carbide. So what are those metal carbides we can have? So typically the range has been told that what are those materials, basically the group of titanium, zirconium and hafnium, then vanadium, niobium and tantalum. So subgroup 14, subgroup 15 and subgroup 16, along with thorium and uranium. So as per definition, we have already selected the group of metal ions which can give rise to the useful metal carbide. So starting from titanium carbide to uranium carbide, we have plenty of those, and they can be used for the different purposes and different useful applications. So now we see how we can process for this particular manufacturing. The first thing what we can think of is the carburization. So carburization of loose or compressed powders of metal or metal oxide. So we will be taking that metal as powder form or the metal oxides, whether they can be in the very loose form, that means form what we obtained, or it can be hard pressed with some pressure in the compressed form with reactive carbon in a protective gas atmosphere. So protective gas can be there such that your carbide should not react with that particular gas. Suppose oxygen is there and the carbon is giving you the anionic form, that means the carbide form through the reduction from the metal ion, because the metal ions will be used for your reducing counterpart, which will reduce the carbon centers to their carbides. So the gas atmosphere should be checked in such a way that your carbon should not be burned as carbon monoxide or carbon dioxide. So this carburization process takes place with a particular process named as Menstrom process. So Menstrom process is nothing but we have to take the corresponding molten metals. So we have seen that the blast furnace we can use for taking out the molten iron. Similarly, those high temperature furnaces can always be useful for getting the molten metals. So these molten metals can also be therefore directly used for getting those carbides. So if somebody is interested to get that, okay, I am not going to prepare only the iron rod, iron bar or iron wires and all these things, but instead I want to make a business of making the corresponding iron or any other metal iron carbides. So we'll go for that, that means the molten metal iron in this particular blast furnace or any other open earth furnaces, high temperature withstand furnaces, can be useful for reaction with the carbon only. So not only iron itself, but some molten iron alloy can be used also. Molten nickel can also be used, as well as the molten aluminium. So the carburization of metal or metal oxide can also be achieved in another process where we use the carbon source as the methane. Methane can supply the corresponding carbon for giving you the carbide of that particular metal. And also the deposition of the gas phase reactions of metal halide hydrogen carbon mixtures. So one process is that your metal oxide or metal can be reacted at high temperature through the use of methane as gas. And the other process, which is known as your CVD process, in CVD process we will be using not metal or metal oxide, but we will use the metal halide, because these metal halides as the metal ions which will be highly reactive, as well as hydrogen and the carbon, because hydrogen is the corresponding material for the reduction process, and your carbon as the source of your carbide. So chemical vapor deposition technique is the technique for metal carbide preparation using metal halide, hydrogen and carbon mixtures. Then the different types of furnaces what we can use, because these are very high temperature reactions for this carbonization reaction. So these carbonization reactions, what we can use for the furnaces. So what are the furnace types you can have? What are the choices you can have for the use? The first one is your gas heated furnace. So we'll use gas for heating the furnace basically, and the same gas, if we require, the same gas can also be used for making the inert atmosphere while we make the corresponding carbides. So the reaction mixture is first placed in a graphite or fire brick crucible. So the crucible is made up of graphite or fire brick, high temperature withstanding fire brick. Then the combustion gas like methane can come and serve as the protective gas atmosphere while we make the corresponding metal carbide. Then one other furnace is the continuous carbon tube furnace. The furnace is of tube shape and is made up of carbon only, because we don't want to take any other material for making that particular furnace, because it is useful if there is some degradation of the carbon part from the carbon furnace also, that carbon can also be utilized for the carbide preparation. So graphite tube basically, that is also a source of carbon, can be, aids as the electrical resistance, and in which the reaction mixture, because it is the electrical resistance can heat up that particular furnace, is continuously transported in boards basically, the graphite boards through the furnace, and hydrogen is used as the protective gas atmosphere. So if we try to burn it in methane, that methane can supply the carbon, then it can have the hydrogen available also. Otherwise you can just give pure hydrogen for the protective gas atmosphere, such that no other type of reaction can take place in presence of that particular hydrogen gas. Then we can have the high frequency induction furnaces. So inductively heating furnace, and we use the high frequency for that particular purpose. So graphite crucible, again like that of your graphite tube, will be using graphite crucible over there for that particular furnace making, and is sealed under high vacuum. So high vacuum sealing process is done, so you don't have any protective gas atmosphere there, and heated with the induction coil. So electrical induction coil is used for heating process, and coupled with a very high frequency electrical source, electrical frequency, and the temperature up to 2800 degrees centigrade can be achieved. So in this particular case, that means in this third category of this particular furnace, we will be able to reach a very high temperature of 2800 degrees centigrade. That means we will be able to make some more harder carbide materials, more harder metallic carbide materials or hard materials, because once you make that at very high temperature, the material itself should be very high, and it can have very high temperature withstand capacity also when we will be using as their applications. So the metal ion based first example what we have seen, that can be your titanium carbide, and that titanium carbide can be manufactured basically from pure titanium dioxide. So the rutile can be your source as the corresponding ore of titanium. Ilmenite is also well known. So these two ores can be very useful, or can be used directly basically for making titanium carbide. So the use of this particular thing for making titanium carbide is the use of that metallic oxide. Just now we have seen that we can use metallic oxide for this purpose. And like lamp black, we can also use carbon black. So C is there, the carbon source is from the carbon black. And what type of furnace? The induction furnace. So this induction furnace, and not at 2800 degrees centigrade, the temperature in the range of 2000 to 2200 degrees centigrade is sufficient for this particular reaction. So your TiO2 will react with 3C, because this is the reaction stoichiometry. If you try to write down the reaction, if the balanced chemical reaction will immediately tell you that will give you TiC. The formula, the solid state formula, the solid state stoichiometry of the carbide is simply the TiC only. So this TiC will be formed along with some amount of carbon monoxide. So, two part of the carbon is utilized for formation of carbon monoxide and one part is used for converting your titanium to titanium carbide. Then what we can have also, that particular one can be very useful as thin layers of titanium carbide on cemented carbides also, that means the cementing of that particular titanium carbide material increase the abrasion resistance. So, it can be used as an abrasive. So, abrasion resistance power can increase an application as a cutting material. Like silicon carbide we know as a hard material. So, the metallic hard material we are now talking about. So, the example of the metallic hard material is that of your useful cutting material of different type or different property and different temperature withstand or stability is your titanium carbide. So, thin layers, very small layer, 5 to 8 picometer of depth of titanium carbide or titanium carbide nitride, the mixed, when carbon is there and nitrogen is also there. So, titanium carbide mixed can be deposited by chemical vapor deposition process by thermal decomposition of titanium chloride in a methane and hydrogen atmosphere. So, both these as well as the titanium carbide can be deposited. So, if we have the nitrogen source only, then it can be titanium carbide nitride is a mixed form of that. Otherwise, the decomposition of titanium tetrachloride basically and supply of that carbon for the carbide end from methane can be achieved with a mixture of methane and hydrogen for this particular thin layer production. Then the analogous way of making can be used for your making the next material after titanium is the zirconium. So, zirconium carbide, if you see, is a powdery material, is very close in look wise to that of your activated carbon. So, the black mass of this particular, because most of these carbides are in black in color, they are gray in color most of the time. So, they can be confused with that of your activated carbon. Oh, so, this particular one through carbothermal reduction, that carbon is the reducing agent and thermal is the high temperature process of zirconia by graphite. So, graphite will be consumed for making that carbide and is this particular densified zirconium carbide is made after that particular processing by sintering the powder of zirconium carbide. So, first you have the reduction, the thermochemically or the carbothermal reduction at a temperature you get through that graphite, and then your sintering process at a temperature of 2000 degrees centigrade. Then next one, that means of the chromium group is the chromium carbide. So, when you get this particular chromium carbide, then you can have the corresponding chromium salt for this particular process. So, if we consider the corresponding chromium carbon phase diagram, because the phase diagram can only tell you that what are the different stoichiometry or the different composition of these carbides can have the stability and can be separated from that particular reaction of a chromium melt with that of your carbon. So, basically the corresponding stability of those components can be known from the phase diagram only, and that typically tells us a very complex one. The first one is typically a complex one, which is a chromium 23 carbon 6. So, Cr23 and C6 material is typically a different type of material unlike other one, which is Cr7C3, Cr2C2. So, the most simplest one is therefore your Cr3C2 that can have typically the industrial importance. Otherwise, what we can see that what are the other high variety of that chromium content material is available and is formed basically when you have the component, heating component of chromium and carbon. So, the last one, that means the Cr3C2 can be manufactured by carbonization of again the metal oxide, the chromium oxide, that chromium trivalent oxide Cr2O3 under a hydrogen atmosphere now. So if you have the carbon source as the graphite, so again you can use the hydrogen atmosphere for this particular. Then we can have the molybdenum carbide. So the molybdenum carbides are very useful, we know, and one particular form, basically the formula is MO2C now. So the formula of that carbide is different because the solid state formulas are all the time is different, and that depends on how you consider carbon. So if their carbon is 4-, so molybdenum can be considered as the bivalent one. So the different varieties, what we know that we can label it as the alpha form, beta form, and the gamma form and the delta form. But the molybdenum based industrial cutting tool, basically industrially they are also very much useful to make them as the cutting tool. So we'll use molybdenum to get the corresponding molybdenum carbide. So it has typical applications as the cutting tool. And like other, we can also take that corresponding oxide. So molybdenum trioxide, which is hexavalent, or metallic molybdenum itself, because in one case you have to consume, you have to reduce that particular oxidation state of the molybdenum from molybdenum 6, or you can use the molybdenum in the metallic state, which is molybdenum 0, with simply the carbon black in a temperature range depending upon your source, whether you are using oxide or the metallic molybdenum. A temperature in the range of 1350 or 1800 can be useful, and which can be achieved in carbon tube short circuit furnaces. So a type of furnace made up of carbon, and the electrical heating is that of particular temperature rise also can be achieved through short circuit of the electrical connections under hydrogen atmosphere once again. So hydrogen is basically giving you the reducing atmosphere, because your carbon, what is available from there as the carbon black, should be reduced. So this reduction of this carbon, basically if you have not sufficient molybdenum is available for the reduction of this carbon, hydrogen is being consumed for that particular reduction process. Then tungsten carbide, WC. The tungsten carbide can be also available to us while you react it or use it for the reaction with the tungstic acid H2WO4 or WO3, the tungsten oxide, hexavalent tungsten oxide, or ammonium paratungstate, the polyoxometallates. We know the ammonium paratungstate. So anything, we can start from tungstic acid, tungsten trioxide, or ammonium paratungsten, again with that of your carbon source with hydrogen at 700 to 900 degrees centigrade to high purity tungsten powder. So first we get the tungsten powder through hydrogen reduction at 700 to 900 degrees centigrade, then that powder will be consumed for making carbide. So we are not directly using the oxide or the other variety for making your tungsten carbide. Then an induction furnace can be bought, or electrical resistant furnace can also be used for the carburization process. So the carburization process, in all other cases we see that whenever we make the carbides, it is the process is your carburization process and is performed at 1500 degrees centigrade in vacuum or under hydrogen. No atmosphere or hydrogen atmosphere. Then we get through this particular reaction the ultrafine tungsten carbide, which is being manufactured in a plasma at 3000 degrees centigrade. So if we go for very other quality, that means the fine quality, the ultrafine quality of your tungsten carbide, so that ultrafine quality of tungsten carbide can be obtained by simply going for a high temperature reaction. So the plasma temperature is fine. So you use a plasma, so definitely it is a costly affair, but the ultrafine tungsten carbide have some special use, special purpose material, so we can consider that we can go up to a temperature of 3000 degrees centigrade. So at this particular temperature, what you see now, that WO3 will be reacting with carbon monoxide. If we can get carbon monoxide through graphite or oxidation of some other carbon matter, or again the thing what we are using, what we are seeing is your methane. So these two basically giving you your tungsten carbide, or the other part what can be obtained when you use methane, you get water molecules, or otherwise is typically the carbide, and your hydrogen atmosphere can take that oxygen for your hydrogen as water. Then we will see that how we get the metal borides. So carbides, borides and silicides, these were our hard materials that we are trying to cover in this particular class. So this has also very high melting points, great hardness and decent electrical conductivity, because the electrical conductivity is not very high like that of your carbides, and chemical resistance also of moderate character. So these are slightly softer material compared to your carbides, and like those, like that of your carbides, here also a big list of those, starting from titanium boride to tungsten boride. Only thing you should always be careful when we talk, when we give the corresponding informations in a large number of compounds. Basically these are prepared in the industry, that can be very useful also in the industry, that the formula of those compounds. So whether it is a titanium B2, TiB2, or it is W2B5. So the manufacturing process what you can have in our hand are the 5 types. Is the melting of the metal boron mixtures in arc furnace can give you that, or sintering of compressed metal boron mixture. Directly we can take the metal and the boron mixtures and we go for the sintering process, or the reduction of the mixtures of metal oxide and boric oxide, or B2O3. So this boron oxide, or the boric oxide, sometimes people also tell as a boron oxide, basically B2O3 with aluminum, silicon or magnesium. Then reaction of metal oxides with boron carbide. So carbide to carbon containing borides. So these metal oxides with some boron carbides, basically we can have, we know that the BC we can have. Then we can go for the corresponding carbon containing boride making also is a particular process, or deposition from gas phase reaction of volatile boron and the metal compound. So like that of your carbon, as graphite, as lamp black or any other carbon supply, we get the corresponding carbide. Similarly, the boron can also be supplied. The boron, we all know the elemental boron, even the boric acid or the borax or the boron carbide can also be supplied for the preparation of these borides. Then we will see lastly that of your metal silicides. These are not well known and well conversant to us also. Particularly we try to see how we can write the formula of those silicides and what are those important silicides from the entire periodic table. So like that of your carbide, like that of your borides, silicides can also be of preparation processes, then utilized industrially in the different metallurgical fields in which they are scaling corresponding resistance and chemical resistance are important. So their scaling resistance and the chemical resistance are of different type compared to your carbide or boride. So that's why they are the special purpose hard material metallic type, and they are basically these from TiSi2 to W2Si5. So you see like your carbide, boride and all these things, the number of Si unit as silicide unit as the negative part of the silicon to the metal is different. So you should be able to try to write these, because most of them are MSi2 type, mostly all of them are MSi2 type. Only exception is that of your tungsten one, so it is W2Si5. So this typically more number of silicons are there, and the tungsten number is not 1, it is 2. And they are basically deposited using CVD processes as per example as protective layers on high melting metallic surfaces. So, through chemical vapor deposition, metal silicides can be obtained on different high melting metallic surfaces. So, it's basically a protective layer because the metallic surface from its degradation, from its environmental degradation also, or acid resistance or reactivity with the acid can be protected through a coating of these metallic silicides. And this molybdenum silicide MOSI2 is utilized for electrical heating elements. So, high temperature electrical heating material can also be obtained only with MOSI2, which can be operated at temperatures up to 1600 degrees centigrade in air, because it can have the typical coating of your quartz type SiO2, because we know that the quartz can have high temperature withstand, but the metallic hard material what we are using having a SiO2 coating also can also be useful in that particular purpose of electrical heating elements. So, all these carbides, borides and these silicides are very useful high temperature withstanding and chemically resistive material of industrial applications. Okay. Thank you very much.